I have a first question or discussion for you guys is for our day, Brenda bakes chocolate chips and low-fat oatmeal cookies in her bakery. And she uses different amounts of butter and oatmeal in each recipe. So Brenda has 47 kilograms of butter and 140 kilograms of oatmeal. We're wondering how many batches of chocolate chips and low-fat oatmeal cookies can Brenda bake. And there's a diagram which talks about which shows the relationships of the butters and oatmeals for the recipe of chocolate chips and the recipe of the low-fat oatmeals here. So maybe first think about whether there are any relationships for each one, and for the relationships we can derive some equations or linear equations here. And of course we want to set some variables here, so some unknown things here. So we have a table here, which means that for each, actually the C here will be the batches of chocolate. So this means that for maybe one C, I will consume 30 butters and 8 oatmeals. And maybe for one S, I will consume 2 kilograms of butters and 29 kilograms of oatmeals here. So if I'm setting here, I can see those are how per chocolate, like batches of chocolate chips or batches of oatmeals will cost. The raw, the materials here. And the material would be butter and oatmeal in this case. Okay, so we know that the total amount of butter we have is 47, and the total amount of the oatmeal we can use will be 140 kilograms. So we cannot use more than that amount. And then, of course, we want to use as much as possible we have, right? So maybe I can say that I don't know about the C here, but I think maybe I just produce one C. One C. Maybe instead of saying 1C, I say C equals to 1. The amount of butter I will use will be 13. And the oatmeal I will use will be 8. And oatmeal, I would just say. But what about if I still have the S? I produce one batch of oatmeal, like oatmeal cookie here. So S is also equal to 1. So the amount of butter I will use for this recipe will be 2 butter. And the oatmeal I will use for this recipe will be 29 here. So the total amount of butter here I will using is 15. And the total amount of the oatmeal I will using will be 37. What about I increase the C to a larger amount, or I increase the S to a larger amount? Can I talk about anything? So by this relationships, I can rewrite it to actually 30C, and this will be 30 kilograms for each C plus 2 kilograms for each S. And I want to use as much as butter I want, or maybe all the butter here. So maybe the value here should be 47, because I want to use all the butters here. I don't want anything, like any butter to left. And similarly for the oatmeal, like the oatmeal I have. For each production of one batch of chocolate chips, I will consume 8 times C oatmeals and 29 kilograms per each production of batch for oatmeal cookies, which will be 29 times S. And I want to use as much, or maybe all the oatmeal materials here. So it will be 140 here, okay? And now I can solve for the C and S probably, and the value I'm solving here will be some amount of the amount of the batches of chocolate chips I will be producing, and the amount of the batches of oatmeal cookies I'll be producing. That will consume all the materials here. Okay, so the next thing is I want to solve for this linear equations. So let's jump to this one. This is the equation I have. And instead of saying C, I use R to represent the butter, and the S to represent the oatmeal here. And not the oatmeal, but the R should be the chocolate chips that is producing. S is the oatmeal cookies produced. Chocolate, I would say. Okay. And can anyone suggest any method to solve for the values I'm looking for this linear system of equations? How can I find the value of R and S satisfy for both equations here? So first we have said we can graph the 2 lines here and finding the intersecting points between the 2 graphs. That's the first method. And second method is maybe we can use S to represent R. So maybe for the second one, for second equation, we can get that R equals to 400 minus 29S divided by R. And then we can plug in this one into the first equation to get that 13 times 400 minus 29S over R over 8 plus 2S equal to 47. And then we can solve for S, and then we can solve for R. That's the second method here. But now, for this question, I will introduce a new method. So I will go over the solutions here, and the new method will be called the elimination. So it will be the third method we are talking about today. Let's see. Elimination. So by elimination, basically the idea here is we want to reduce the amount of variables, the variable. And how we reduce this, we can compare the two functions here. So for the first one, maybe I want to change those to some things like 13R plus something equals to something, and then it will be 13R plus something equal to 13 equals to something, and I'll make those as the third and fourth equation. And after making them the third and the fourth equation, I can simply subtracting the third equation by the fourth equation, so that we don't have any R variable left. So that's the idea here. And how we do that, I would say for the first one, I will do, okay. So let's say the first equation times 8, where is a common factor, because we know that if 13 times 8, and then we times 8 by 13, then they can eliminate each other's. So the second equation will be times by 13. And after doing that, I can do times 18 on each side. And times 13 on each side for the second equation as well. And then after making sure the equation here looks good, I can do the calculations using the distribution method. So the equation I'll derive will be 104R plus 16S equals to 1820. And the next equation I will derive will be similar 104R plus 377S equals to, this one should be 182, and the above one just making these mistakes, which is 376, just by calculating like using distribution method. And then now I will label the two equations, one as equation 3 and one as equation 4. And after labeling those, I will say I will want equation 3 minus by equation 4, where we will just do a subtraction. So 104R plus 16S. To change the color for this one. Here's from the first equation minus by the parts from the second equation. Plus 377S. And then we can do similarly 376 minus 1820, where the yellow parts are from the first equation. The subtraction is the operator here, and the orange part is from the second, like the fourth equation here. And after subtraction, I can say like you open the bracket here to do further calculations. Minus 377 as equals to 276 minus 80-20, 18-20. And I can eliminate the variable r here to make s only. So the final equation I will derive will be negative 361s equals to negative 144. And I can easily solve for the value s now. And then I can also solve for the value of r. We're plugging the s equal to 4 back to any of the previous equation. I can derive that r will equals to 3. So that's the elimination method here. We just like want to use two equations only by maybe finding some common factors to eliminate the value r, or maybe you can eliminate the value of s, and then we can solve for the other variable separately. Okay, this is just another method which are just like eliminating a different variable. We are starting to eliminate the variable s instead of the r here. So I will, for this one, I will ask you guys to try by yourselves, try to think about which number we should multiply for each equation to eliminate the s here. So the 29 is derived because bottom is 29, and the second one will be 2 because the first one will be 1. Okay, that's perfect. That's correct. Definitely correct. So the first one, we are just like multiply 29 on each side of the equation, and then multiply the second equation by 2 on each side as well. And it is equal to 2 times 140 here. And now let's simplify the equation. We'll calculate the result here by opening the bracket. So we'll have 377 r plus 58s equals to 1363. And the lower one will be 16r plus 58s as well. And on the right hand side will be 280. Yeah. Okay, now what's the next step? Let's label them as maybe equation 3 and equation 4. So we just subtract the two equations. So by subtracting, it means the left hand side subtracted by the other's left hand side, and right hand side was subtracted by the other equation's right hand side. So we have 377r plus 58s minus 16r plus 58s. And remember, there should always be bracket because we are subtracting the entire side of it. Minus 280 here. And then we can open the bracket. While we are open the brackets, this plus will become a subtraction for this 58. So actually I can just copy and paste the things here. So open the bracket, the first one can directly open, but the second one, the plus should be changed to a minus here. And for the right hand side, we can directly open the bracket. And finally, you can find out the 58 can be subtracted, like the net positive 58 will be subtracted by the other 58 as here. So we eliminate the as variable in this equation, and we just simplify the entire equation or find the like items to add or subtract them. So in this case, it will be 361r equals to 1083, and we can derive that r will equals to 3 as well, and then plugging back to any of the equations, we can derive that as will be 4. So by plugging back, I mean we can plug in this 3, replacing the r value here, so it's 13 times 3 plus 2s will equal to 47, and then we just solve for s, and s will still be this number 4. So by eliminate the equations, we can literally eliminate any of the variables as far as we can find the numbers to multiply for each equation properly. Any question about eliminating any variables here? Good, okay. So this is just like a more solution here. So there's actually some steps while we're doing elimination. So this will be actually similar to what we have for the substitution method. So remember, always name our equations by some letter or labels here. So maybe 1 and 2 for the linear, like the equation, like system of equations here. And whenever we have new equations, we are always label with the new numbers, maybe 3 and 4 later. And while we are adding or subtracting the equations, we can always directly use a label to add them or subtract them. So maybe equation 3 plus equation 1 or equation 3 minus equation 1, just as what we have done. And of course, while we are dealing with the equations, the variables will always be the same variables. So the x variable will be the same x variable for the other one, because we are solving for exactly just one x variable or y variable as well. And always try to like check our final answer by substituting our x and y values back into the original system of equations. So that's making them consist, like the right-hand side should always be equal to the left-hand side for all the equations here. And that will just be some suggestions or tips. And I have several practice here. So for this practice, I will ask you guys to finish after the class because we are a little bit rushing. Maybe we can finish this using one, like try to eliminate just one variable during the class, and you can try to eliminate the other variable after the class here. So try to think about how we do the steps here, and maybe think about the labeling as well. So that's what be the like sublinear equation using elimination method. So basically, this will be similar to what we have for substitutions, and you can see sometimes it's weird as we have just mentioned. But sometimes it would be super helpful as from the previous example, you can observe it as well. And lastly, I want to do the exploring the linear systems, and that's what will be the final unit for chapter 1. So by exploring, I want to explore some solutions. How many solutions can a linear system have? And how can we predict the number of solutions without solving the system? Yeah, sure, go ahead. So basically, we want to know about the number of solutions without solving the system itself. So anyone have any ideas to think about the number of solutions for linear systems? And maybe try to think about the number of solutions for the first system, second system, and the third systems here. How many solutions they have? So actually, I have a table here. Is some steps you can think about, and you can go ahead if you have ideas. So basically, we actually just rewrite it to y equal to mx plus b to better examine what the line itself looks like. But the idea is we will basically have 3 solutions. So case 1 is will be two intersecting lines. So the graph looks like one line, let's say L1, will intersect with the other line, L2. And the second case, so by this one, like it means that they will have one solution. And the solution is the point of intersection. Case 2 will be 2 parallel lines. And for 2 parallel lines, they are actually, I would say, and non-coincident. So by coincidence, it basically means that they will be the same. This can means like the same line. Or one is lying on each other's. So by non-coincidence, it means that not the same line. Sorry for that. And by coincident, it means the same. So in this case, it will be 2 parallel lines, line 2 and paralleling to line 1. In this case, we can see there's no point of intersections, therefore there will be 0 solutions or no solution if they're parallel to each other. And the last case will be similar to case 2, but a little bit different. So it will just be what students have mentioned. It will be 2 parallel lines as well, but coincident, which means that they are the same line. So one line, let's see, one line L2 well lies on the other line L1, or they'll be the same line here. So those are the three cases, or the number of solutions for linear systems. And how we can determine them, as previously mentioned, we can first examine the slope. Oops. If the slopes are same, which means that the two lines must be parallel lines and may probably be the same line. And if the slopes are the same and the intercept or the b values here are the same as well, which means that they are the same line. Just they will definitely produce the same equations. Otherwise, there will be just two parallel lines, and or I can say non-coincident lines here. So those are actually, we have just direct jumping into the conclusions here, how to examine or exploring the linear systems here. So okay, so maybe for the first one, I want to see whether the two lines are the same. Maybe you can try to think about it by yourself or by the method or the conclusion we have just jumped into. So for the first one, can you tell me the slope of each one, or maybe the m value? Why this will be a -2, because we are, yeah, -2 over 3x minus 4 over 3. And the second one will be, yeah, and actually we are plussing this to the right hand side, and then we finally subtract by a negative, so we just change the signs here. And we can see the slopes here, they are not the same. So the slopes here are not the same, which means that m1 not equals to m2, which means that only one solution where they must intersect. And for the second one, I will just for the second system equations, I will just directly get them. So it will be y equals to -3 over 2x plus 3. And the other one will be y equals to -3 over 2x plus 5 over 4. So for this one, we can see that m1 equals to m2, but b1 doesn't equal to b2, which means that they are starting from different initial values, and this means that they're parallel, so there will be 0 solution for the second one. And for the last one, there will be actually the same equations, because as you can see, we are just multiplying 3 for each side of both equations here. But I can also always write it to the standard form, so it will be -x minus 5 and y equals to -x minus 5 as well. So there will be infinite solutions here, because m1 equal to m2 and b1 also equal to b2 as well. So they're indicating that they're the same line. Any questions here? Okay, great. So there's conclusions as well, and you can see it's just the graph they have just drawn. So for the first one, it means that they will have no solutions. I'll just highlighting the conclusion as well. Has no solution. Oops, that's too large. No solutions. Why? Because the m1 equals to m2, but b1 doesn't equal to b2, which indicate that they are parallel lines and non-coincident. Where the second one will have only one solution, because they will just be intercepting m1 doesn't equal to m2. And for the last one, there will have an infinite number of solutions, because m1 equals to m2 and b1 equals to b2, which means that they are parallel and also coincident. 3 and or I can also say that they are a same line. So those are just conclusions or the graphs for each for the linear systems here. And that's what the only 3 cases having each other linear systems as well. Any questions about the linear systems here? If there's no questions, we are finished the first chapter and we'll jump into the second chapter as well. But before that, as we have reached an hour, so maybe we can have a 5 to 10 minutes break. And maybe I can see you guys 8:30. And you can just drink water or do whatever you want during the breaks. So we'll be back to class at 8:30 here.